Hello everyone, I'm Jiatong Li, an undergraduate student from University of Science and Technology of China. Today, I'm going to share our work at KDD22, the HierCDF, a Bayesian network-based hierarchical cognitive diagnosis framework. My presentation consists of 5 parts: the research background, the related work in cognitive diagnosis assessment and Bayesian networks, the introduction to our proposed approach, the experiment, and the conclusion. Cognitive diagnosis assessment is an important task that aims at diagnosing students' cognitive level from their response logs. In cognitive diagnosis assessment, attributes and attribute hierarchy play a significant role because they illustrate how a student cognizes and exercises. Attributes are necessary skills or knowledge concepts for students to correctly answer questions. Attribute hierarchy is a graph that reflects the cognitive dependencies among attributes. However, there exist several problems in the research of cognitive diagnosis assessment. First, most existing cognitive diagnosis models ignore the existence of attribute hierarchy. Second, existing attribute hierarchy method is time-consuming and impractical when facing a large number of attributes. To this end, we designed a Bayesian network-based hierarchical cognitive diagnosis framework to efficiently diagnose students' cognitive level from attribute hierarchy. We then validate the generality and efficiency of our model by analysis and experiments. In fact, there exist two main lines in the research of cognitive diagnosis assessment. In the first line, cognitive diagnosis models estimate students' ability without attribute hierarchy, such as item response theory and neurocognitive diagnosis. In the second line, however, cognitive diagnosis models like attribute hierarchy method estimate students' ability based on attribute hierarchy. In the first line, for example, item response theory models student by scalar and utilizes a logistic-like function to estimate the probability of a correct response. As another CDM, NeuroCD models students by mastery probability on every attributes and capture the complex interaction between students and exercises with a positive neural network. In the second line, attribute hierarchy methods limits that the mastery level of a parent attribute should be no less than that of a child attribute. The set of mastery patterns that satisfy the limitation is the latent space. The model then classifies a student to a mastery pattern that has the largest probability of generating her response log. Bayesian network is also an important related work in our research. It is a probabilistic graphical model used to reason and infer relationships between entities organized in a directed acyclic graph. If we see attributes as nodes and attribute dependencies as edges, students' mastery on attributes can be modeled by a Bayesian network. As shown in Figure 3, the joint probability can be modeled by conditional probabilities, and the marginal probability of any node can be modeled by the formula of total probability. Here, we introduce some preliminaries. The first is the definition of our task. Given data above, our goal is to mine students' attribute mastery pattern and the dependence relationship between mastery of attributes in the attribute hierarchy. We then give the definition of two assumptions. The first assumption, the hierarchical cognitive assumption, says that the mastery of a parent attribute is the prerequisite of the mastery of the child attributes. The assumption is theoretically based but lacks the support of data. The second assumption, the monotonicity assumption, says that the probability of correctly answering an exercise is monotonically increasing at any dimension of the student's attribute mastery pattern. It is important for the interpretability of CDMs. This is the structure of our proposed model framework, the HierCDF. It consists of 3 modules: the cognitive state module, the question feature module, and the CDM adapter module. The most important part is the cognitive state module. Now, let's continue with making cognitive diagnosis in HierCDF. Given a student, a question, and the response score, in the first step, the model represents the student by conditional mastery levels CI plus and CI minus. Then the model infers the student's cognitive level on each node by attribute hierarchy on Bayesian network. In the second step, the model uses the nth row vector of Q matrix to mask students and question features, and transforms masked features to low-dimensional vectors to adjust to selected existing CDM, such as item response theory. In the third step, the model inputs transformed features to existing CDM to predict response score. Then it optimizes cognitive states and question feature parameters by backpropagation and gradient descent algorithm. Now, we introduce the detail of cognitive state modeling. Given a student Si and an attribute K, the mastery level MIK is influenced by that of parent attributes Mij and attribute dependencies Ci plus and Ci minus. Here, we take a node with two parents as an example. The current node K has two parents, J1 and J2. For each of parents, the student's mastery levels, the Mij1 and Mij2, have been estimated in advance. For each of edges, there exist dependencies C plus and C minus to represent the mastery level of the child node conditioned on the mastery or non-mastery of the parent's node. Then the student's mastery level on K, MIK, is influenced by Mij1, Mij2, Ci plus, and Ci minus. The influence can be modeled by a function G, and the implementation of G varies among the different positions of current attribute node. For each node, we see the mastery level of K as the probability of mastery the node. If K is a root node, then MIK is just a trainable parameter. If K has only a single parent, then MIK can be estimated by the formula of total probability. As shown in the right figure, MIK is influenced by Mij, Ci plus, and Ci minus. If K has multiple parents, MIK is still estimated by the formula of total probability. Here, the joint mastery probability of parents is estimated based on naive Bayesian assumption. Besides, the joint conditional mastery probability is estimated by the geometric mean of C plus and C minus. That's because if we estimate the probability by the product of C plus and C minus, the result will be extremely small if the number of parents is large. Here is an example. The example is the same in page 11. Here, Mij1 and Mij2 decides the value of the joint mastery probability of parents, and Ci plus and Ci minus decides the value of the joint conditional mastery probability